So talking about secant lines, tangent lines, average rate of change, instantaneous change is all built up for establishing a definition for what we mean by the derivative. So when we talk about the derivative of some function f at x, which we notate as f prime of x, there are a couple different notations we'll look at a little bit more in the next module. But for right now, we'll stick with this f prime of x. So that's sort of an apostrophe, a tick mark there. And we would read that as f prime of x is just the instantaneous rate of change for our function at some given point x. So f prime of x equals the limit as h approaches 0 of f of x plus h. So now instead of a plus h, we're just saying for any possible value of x minus f of x divided by h. So that is our definition for the derivative if that limit exists. Then f is said to be differentiable. There is a 4-step process that your book introduces for applying this definition to come up with our derivatives. So we'll look at using the definition broken up into a 4-step process. So the first step is to evaluate f of x plus h. So rather than trying to tackle that definition as a whole, we're going to start off with just breaking it piece by piece. So we're going to take this expression x plus h, substitute it into our function, and see what result that gives us. The next step then will be to take that result we came up with in the first step, f of x plus h, and subtract the original function, f of x itself. So we'll subtract the function, simplify, combine any like terms, whatever we can cancel out. In our third step, then, we'll take the result from the previous step, and we'll look at what f of x plus h minus f of x divided by h is. So we take the result from step 2, divide that by h, and again, as much as we can, simplify. And then in the very last step, we'll take the limit as h approaches 0 of f of x plus h minus f of x divided by h. So these are similar to problems we looked at when we were doing limit problems. We can't take the limit of this function using direct substitution because we get a 0 in the denominator. So at the end of this third step, the h in the denominator should cancel. So that when we get to this last step of taking the limit of that function, now through all of our simplifications, cancellations, now we'll have a limit that we can evaluate through direct substitution. So we have a definition for the derivative, but it's important to understand that the derivative for a function may not exist at one or more points. So a function is said to be non-differentiable at a specific point, x equals a, if the following limit does not exist. So if we consider the derivative of our function f at a, so f prime of a, equals the limit as h approaches 0 of f of a plus h minus f of a over h is a limit that does not exist. So visually what this means for the derivative to not exist, our derivative can fail to exist, or that limit can fail to exist, if our function is discontinuous at some point x equals a. So this could be if we have a break in our graph, so here we have a break in our graph. At that point, our function would be discontinuous. Or if we just have an open hole in the graph, again, here at this open hole, the derivative would fail to exist because this limit would not exist. We can also have a case our function is differentiable if we have a sharp corner at x equals a. One example of this happening is with the graph of the absolute value of x. So the graph of the absolute value of x is going to have a sharp corner at 0. And the reason we would say that the derivative doesn't exist here is because as we approach from one direction, our function is decreasing. But as we approach from the other direction, our function is actually increasing. So our function can't be increasing and decreasing at the same time, at least at that, with regards to this instantaneous rate of change. So we would say the derivative does not exist at x equals 0. Our function has, if our function has a vertical tangent line, at x equals a, then we would also say that our derivative does not exist. So as one example of this, this would be something where our function sort of dips down and then immediately starts increasing again. The third case would be a rare one for us to consider with business calculus applications, but examples 1 and 2 are things we want to keep in mind. If we're dealing with absolute value functions, there's going to be a point where our function is undefined because somewhere we have a sharp corner. And if we have points of discontinuity in our function, either a break or a hole in the graph, again, we're going to have places where our function is not differentiable.